So assume that we have the following more requirements about the carpenter problem. Okay, so he has 3 models of tables, 5 models of chairs. Each model can have different profit. He has 10 helpers. Each one can work on specific models. We have space limitations. We have some fixed number of tables or chairs that we have to meet, no matter what's what we need to do, I mean, to increase the profit. And now the question, how many tables and chairs should be produced? Obviously, you cannot use the same calculation method that we were using before, right? And this is when we use linear programming, all right? So what is linear programming? We will denote that by LP for abbreviation, linear programming. It's a very, very powerful tool used by not only operations managers, by managers from all disciplines. Okay, why? Because we need to obtain an optimal solution for problems. What kind of problems? That involve restrictions or limitations. We call that constraints. And that's why we call these problems constraint optimization problems. So these are problems where I have limitations and I want to optimize a certain value. And when we say optimize, that means we may need to maximize, like we were trying to maximize the profit of the carpenter in the previous example, or minimize a certain cost, a distance, a time, etc. All right. So next I'm going to show you what does a linear programming model consist of. So what's that linear programming models that we're talking about? First of all, I need to relieve some of you guys who may be scared by the word programming. We're not doing any programming like the programming languages that you hear about, like C or Fortran or whatever. We're not doing a programming per se, right? The programming word here is only referred to the to how we are organizing our mathematical formulations, right? And linear because the functions will be linear, like y equal to x. This is linear. We will not do y equal 3x squared, right? Okay, so that's it. Now, all LP models look alike, no matter whether you are using a model to solve a real life problem where you have thousands of decisions that you need to make, or something similar to what we just did with the carpenter problem where we have only 2 decisions to make. They all look the same. They all comprise 3 components. Okay, the first component is your decision variable. What's that? This is the choice that you have in hand as a decision maker. So the carpenter in our previous example, he had 2 decisions to make, right? What were they? He wanted to decide how many tables to make, how many chairs to make. So because we want to represent the problem mathematically, right? So what we are doing here, we are translating words into mathematical expressions. This is how this is also a major property of linear programming models. It represents a problem, but mathematically, using mathematical expressions. So the first part or the first step is very important. You need to define very well your decision variables. So my decision variables we'll denote them usually with the symbols. It can be a symbol that represents the product that we are doing. For example, C for chairs, so it's not a coincidence, and this is a T for tables, right? It's good to use these symbols that really help you directly know which variable you're talking about. So this is it. It's the number of chairs to make daily. You cannot stop by saying C is number of chairs. What number of chairs? The number of chairs that I want to make on a daily basis, right? Because, for example, what if you are trying to find how many tables, chairs or table to make on a weekly basis? It will be different. approach, it will be a different model that you're going to end up with. All right, so that's why defining the variable is a very important step of linear programming modeling. All right, so here we go. Second component is our objective. What's that objective? It's what we are trying to achieve, and this is what trigger you to start using NLP model. In the carpenter problem, the carpenter wanted to maximize his profit. Now, with many requirements, many limitations that he has, he could not do it manually, and he wanted to revert to an NLP model to do it for him. And usually an objective is either a maximization or a minimization. Okay, and how do we represent that in the LP model? We represent that into in the objective function, which is also another mathematical expression. So again, remember, we are trying to translate words into mathematical expressions in order to present the problem in a mathematical model. And this also define for you or explain for you why we call it programming, linear programming. All right, it's the way that you present your problem. So in the carpenter example that we just did, what was the objective? Of course, it was we wanted to maximize the profit. All right, so how do we represent that in an objective function? First, let's see the mathematical method how to find the profit. It's very easy, right? What's the profit? It's the profit per unit for every chair you multiply by the number of chairs. And remember that we defined C as being the number of chairs to make. So when I multiply the number of chairs by $20 per chair, I will get how much profit I can get from the chairs. And when I multiply $30 per table by the number of tables, I will get the profit that I get from the tables. So the total profit is 20 times C plus 30 times T. So how to put that in my model? I will simply want to add one thing. I don't need to write P equal that. No, I will represent my objective by specifying what I want to do with this function. I need to maximize this function, right? So the software will be changing these values, C and T, in such a manner that the whole thing here will be maximized. The third component is the constraints. What are constraints? These are limitations that would limit, like the word imply, that would limit our options. Okay, and we have seen that in the carpenter problem. I will come back to that anyway. But first of all, let me tell you that mathematically we have three types of constraints: those that use the inequality less or equal, greater or equal, or equal, right? So they are specifying for us that, listen, this should be less or equal than that, or it should be greater or equal than that, or even harder, it should be exactly equal to this. All right, now constraints usually they are very important because they define what we call the feasibility of our solutions. Remember when we were doing the carpenter problem, each time I was adding a requirement, I was asking you the question, does the previous solution is it still applicable? And I use the word, is it still feasible? That means, does it still meet the new requirement as well as the previous requirement? And that's why we were changing it, right? So all the set of the constraints will form for us what we call the feasible solution space. What is it? It's all the options that we have, all the solutions that we have, where all the requirements are possible. Here we're talking about solution, and it's a term that I used also in the carpenter problem. When we say solution, it's only the set, the combination of the values for the decision variable that will maximize the profit. All right, it's not necessarily maximize, that will meet all the constraints. Now, if it maximizes my objective, it's called the optimal solution. All right, so what are the constraints that we had in the carpenter problem? First, the time constraint. What did we say about the time constraint? We said that the carpenter has 10 hours a day, and every chair requires 1 hour, and every tables requires 2 hours. So what I wanted to represent that like that. I wanted to say that, look, all the time that you put working on the chairs plus the time that you put working on the table should not exceed the available time of 10 hours. Now I'm approaching more to the mathematical representation for that. All the time that you put to make on this chair, I know that I'm making a C number of chairs, and every chair requires 1 hour. So the time that I want for the chairs is 1 times C. So if I want to do 3 chairs, this will require 1 times 3 hours, right? You can see that. Plus the time that you put on the tables, number of tables is T. It can be 5, it can be 10, it can be 0. It's any number. Okay, multiply that by 2, which is the number of time required for one table. So if I'm doing 4 tables, I need 2 times 4, 8 hours for that. So the time that you put on the chairs and on the table should not exceed what you have, which is 10 hours. And that's my time constraint. You see, very simple. Second is the wood constraint. Similar logic. I multiply 0.7 because this is how much I need for every chair, multiplied by C, plus 1 meter square per table times T should be less or equal than 4, which is the available wood for us. And finally, the truck capacity constraint. Also, I multiply 0.8 meter cube per chair times C, plus 1.5 meter cube per table times T. The whole thing should not exceed 5.5 meter cube. And that's it. With the decision variables defined, with the objective function put into a mathematical expressions, and now we have the 3 constraints in mathematical expression. You have the LP model ready for the carpenter problem. So in summary, the LP model consists of mathematical expression for the objective function, all right, and one mathematical expression for each of the constraints, as we have seen in the previous slides. Now, these mathematical expressions or statements, they consist of symbols and numbers, right? The symbols represent your decision variables, like the time constraint, I was writing 1 times t. So we have the 1, the number, okay, the numerical values, times t, times c, which is the decision variable, plus 2, number again, times t. Okay, and what are these numbers? They are parameters. They are given to us. Okay, and we do not come out with these values. They are given to us.